welcome everybody to Frigid February FPGA seminar. So today we have a talk that will be somewhat a rehearsal for an FPGA presentation. There'll only be a poster there, but we'll give Naif a chance to talk about the work that he's doing. So this is work that we've done to kind of expand OpenFlow using some of the virtualized FPGA hardware that Stuart Byma developed previously, and Naif is now taking over that project. So Naif will describe what's happening here. So we've got to be on this side.
Yep. Cool. All right. So yes, just disclaimer. This presentation was normally a 5-minute presentation, but over the last couple of days, I tried to expand it to hopefully 20 minutes. So we'll see how effective that is. So in a nutshell, we're expanding OpenFlow, which is a software-defined networking open source standard with the virtualized infrastructure that Stuart has made before. So probably a lot of you remember that infrastructure. If not, I'll briefly go into it later on in this presentation. And yeah, so our main goal is to expand OpenFlow with the versatility that we get in software and the performance of reconfigurable hardware. So what is software-defined networking? Software-defined networking is basically where this relatively new paradigm where they separate the control plane and the data plane, where the control plane is typically in software and the data plane is typically in hardware. So you have a bunch of these really cheap commodity switches rather than your typical expensive network switches. And the abstraction is similar to what we picture with an operating system in a typical computer architecture, where you have your operating system abstracting away the lower level details. It's similar to how a NetworkOS abstracts away the lower level details of these switches. So I'll go to the next slide, which has a nicer picture. So you have your NetworkOS, which is logically it's one centralized layer, and underneath it you have potentially several different network switches. These could be geographically close to each other. These could be geographically far from each other. The NetworkOS has all those details. And on top of the NetworkOS, you have control programs, which are network applications. So we'll get into what these network applications could be a little later. These network applications communicate with the NetworkOS. The NetworkOS sends these things called flow tables, which pretty much on a low level to each one of these switches describes how to take the ingress packets and where to forward the outgoing packets, whether to drop packets, and it bases it on these things called flows. A flow is described with a header and an action. So ideally when they projected the idea of OpenFlow, they are picturing this really arbitrary header where I can say, hey, you know what, I'm not restricted by this network protocol. Look at the first X bytes of this. This will make my new header, like it could be TCP, it could be IP, it could be my own thing. And now based on this header, forward it to whatever, this port or that port. Now, all that support is not there. Right now, it's restricted to MAC addresses, UDP addresses, and somewhat standard protocols, but you can still define your own actions here. And so OpenFlow is this open software-defined networking protocol. And like I said before, it works with flows, which is a description and an action. Now, these flows are translated from, if we look in the previous picture, these control applications, depending on how the NetworkOS is set up, there's a lot of research going on how to set up these NetworkOSs. So it's usually follows the structure, may or may not exactly follow what I have here, but it can convert what you have here into these lower level packet details. So a lot of times this control program doesn't depending on how the NetworkOS is set up, doesn't even have to know where these guys are. It can say, hey, you know what, chunk out this part of the network. And this NetworkOS is going to do those low-level programming details. So again, this is what a typical flow looks like. you have this rule. It could be exact or wildcard. So I copied this slide from this professor's slide. He's a professor here. So the rule describes, again, the kind of header that you're expecting, and this action can be forward it, drop it, or send it back to the controller. So this last action it can be quite problematic. So as I said before, you have these things that are really fast in hardware, and logically you have a centralized operating system, like a NetworkOS. So you can imagine if you see this last rule, if I don't know what the header is, send it back to the software controller. That could be quite problematic, which is where if you don't have OpenFlow support to support a kind of header that you're expecting, and it all gets sent up to the NetworkOS, that could be slow, that could even crash your network, and from my experience, that has crashed my network, so it's not fun. Okay, so that was a brief overview of what software-defined networking is. I'm gonna crash course you through cloud computing. So cloud computing is the idea of where you have this centralized pool of resources and you hide it from the users, and you can chunk it out to different users. And each of these users are unaware of what the resources look like underneath. Their virtual mapping to physical mapping ideally should be hidden from them. And to them, they see this infinite pool of resources, which they have all to themselves. And each of these users are completely unaware of who else is on this network. Now, the new thing that we've been pushing, which is this idea of heterogeneous cloud infrastructure. So an example is what we have in the Savvy network that's in Bayhead. So this heterogeneous network is this cloud computing infrastructure where you have not only your standard virtual machines, you have GPUs and FPGAs. And with that being said, the idea of virtualizing these devices, that's where it becomes interesting, because we don't have a lot of infrastructure to do that at the moment. So here's a review of the infrastructure that we do have that was developed by Stuart. So there's two main components. There's this static region and there's this user application region. So the static region is like this shell, which abstracts away the I/O and this cloud management configuration stuff. The user application part is divvied up into, in this case, divvied up into 4 regions where different users can share this FPGA in space. And furthermore, it uses partial reconfiguration to swap in and out these user application bit streams to allow the users to share the FPGA in time as well. And of course, all this is managed by OpenStack. So OpenStack maps out what addresses these user application regions have in the network, and it maps it to what's available in the FPGA. So again, some of the key points is that the virtualization of the FPGAs allows you to share the FPGAs in time and space, and it abstracts away the Ethernet and memory. So how the communication of these FPGAs work is that OpenStack manages this network mapping to each one of these user applications, and the packets come into the Ethernet of that. The FPGAs sit on the network, receiving the packets from the Ethernet, and then the static region actually determines, hey, this MAC address header corresponds with this particular user application, and all of this is managed by the cloud infrastructure that we have. And of course, all of this mapping is hidden from the user. So this is what the big picture of it looks like. So if you see, we have your standard VMs here, and we also have our VFRs, which is this virtualized FPGA resource. So you have potentially multiple user applications spread across multiple FPGAs, and all communicating through this shared network backbone. So I guess to bring back how we combine both of these things, OpenFlow is quite attractive for data centers. So these, like I said before, these dumb switches are much cheaper than your standard fully commercial switches. And the network can also be personalized and customized to allow you to give users chunks of the network. So if the user wants to experiment and run network applications on, let's say, 5 VMs, and he wants to make his own mini network amongst the virtual machines, he can do that really easily with programmable networks. Now, our motivation to combining this with the virtualized infrastructure that we have is that since the FPGAs sit right on the network, it's quite suitable for these networking applications. And secondly, virtualization allows multiple users to share these FPGAs for these networking applications. And we're going to get into a couple of these applications that we're looking at. So one of the applications that we're looking at is implementing this VXLAN. So this VXLAN is a tunnel between two local area networks, and the VXLAN actually the protocol sits underneath UDP. And one of the limitations of OpenFlow is that it cannot see the UDP payload. And due to that, it can't actually make these decisions based off of the information that it has in the VXLAN. So I guess before we get into the application, the way that we send packets into the FPGA is something that we call Flurry Direction. It's simple. It's basically using OpenFlow to instead of having this typical path between two virtual machines, we redirect what was supposed to go to the second virtual machine through the VFR. So it's a standard. It's a pretty simple OpenFlow command saying that, you know what, all packets coming in from this port or with this particular MAC address and this destination MAC address, instead of sending it here, send it out to this port. And this VFR, the mapping that it has is associated with the destination of this packet. And then this VFR then outputs these packets back into the switch, and there's also a flow that describes the packets coming in from the VFR to be redirected to the second virtual machine. So the first application that we looked at is this VXLAN firewall. This VXLAN firewall actually, we implement the VXLAN tunneling first in software, but we do the VXLAN firewall with a virtualized FPGA region. So this VXLAN firewall basically, it drops all non-VXLAN packets and blacklisted packets. So basically what we have here is we have, let's see, where is that? Okay, it's not in the diagram, but in the application we send in control packets to let it know, hey, drop all packets that have this kind of header information. So all of that information is stored in a content addressable memory, and once that's configured, incoming packets that are redirected into the VFR are compared with the blacklisted with the blacklist in our CAM. And if that is a VXLAN packet and it matches something in the CAM, then we know that that's something that we have to drop. Else, we let it go through and it would go to its appropriate destination. Now, some of the results that we see is that, so here's, without the VXLAN tunnel, the throughput that we see is about 900 megabits per second. But as soon as we implement the VXLAN tunnel, this is again, without the firewall, we see that the performance drops to about 517 megabits per second. And then, on top of that, when we, with the software VXLAN tunnel and we introduce a VFR firewall, we see that a slight drop in throughput from 517 to 513 and a slight increase in latency. So that's pretty much what we expect. We expect that this hardware to be processing these packets at almost line rate with a minute latency increase because of the extra network hop. So secondly, the application that we looked at is not just the firewall, but actually doing the VXLAN implementation in hardware itself. So this VXLAN implementation comes in two stages, where you have your packet coming in, and we have one VFR that is labeled as the encapsulator. So this encapsulates the incoming packet with the VXLAN header information. that VXLAN header information is actually the destination that it stores is actually the location of the second VFR, which would be the decapsulator. This encapsulator is configured, again, similar to the firewall application. It's configured with these control packets. So these control packets let this application know, hey, you know what? Whatever packets come in, tack it on with this header. And in this case, the header happens to be where the decapsulator is located. And then the decapsulator strips off that VXLAN packet that came in and sends it to its destination. Oh, sorry, I should have had some result slides. So basically, similar to what we saw before, where we saw on almost no drop in throughput when we introduced a bit of hardware. So from here to here, we saw almost no drop in throughput. We actually saw something similar when we implemented the whole thing in hardware. When we implemented the whole thing in hardware, where the throughput used to be 941 megabits per second, we saw the throughput to be at 938 megabits per second. Very, very, very close. And we actually saw the latency to be about 0.609 milliseconds. So it's exactly what we expect. We expect these packets to be processed in line rate with a slight increase in latency due to the extra network hop. Okay, so some future work that we see is that, well, what this paper has shown is that this infrastructure can be quite effective for SDN applications. So I'm not an SDN expert, and as a matter of fact, I'm hoping to send these slides to an SDN expert who can tell me what some of these cool applications could be. But from the brief research that I did, a lot of these applications can be network monitoring and debugging applications. So if you've ever tried network debugging, you will know that it's not that pretty. And to be able to have extra debugging support on the network is something that is quite common in SDN, and maybe being able to implement this in hardware could make this more effective. Network security. So our simple firewall application is a brief demonstration of that, but I think something like this could be more powerful if we actually use maybe something like the network traffic to automatically determine what kind of what kind of packets to blacklist, and some of these more complex network security applications. And lastly, network load balancing. So if we see a common application with SVN is if you see a lot of packets going into one section of your network, some application automatically determines, hey, this part of the network is being congested, let me redirect it to another part of the network. So these are kind of the applications that we see in this domain space. Again, this is something that we'll have to investigate. And in terms of the virtualized FPGA project extensions, this it's still quite fuzzy to determine that again, but we're looking at implementing more cloud computing features like VM migration, potentially dynamically sizing of these VFRs, and maybe support multiple types of FPGA with agnostic virtualization. So having a large amount of FPGAs on your network without keeping the user completely in the dark with what's actually being physically implemented. We somewhat have that in place, but I think we could probably do a lot more work in this area. So in conclusion, these are some network applications developed in hardware, and as expected, we saw the throughput to be almost the same with a slight increase in latency. The virtualization aspect simplifies the new application stuff. And again, these applications are just the tip of the iceberg. So hopefully we'll have a lot more applications coming soon. So on that note, that concludes my presentation. And yeah, I'll be open for
Difference in speed between redirected and redirected with searching and removing packets is like 3 megabits per second.
Yeah.
That's just noise, right? Like there should be zero difference.
Yeah, there should be
because
zero.
it's perfectly pipelined and
Exactly. So like, I think we ran, I think if we were to run this like 5 more times,
Okay.
you'll see different numbers in the same ballpark. Yes, Bob?
Do you know how much cheaper at OpenFlow's dumb switches? So you contrast the kind of high-end switches versus
Yeah.
OpenFlow dumb ones. I know that's the promise of OpenFlow, that they're going to
Yeah.
essentially commoditize the switch. Do you know, can you go buy an OpenFlow switch today that is much cheaper than a Cisco switch? Because also Cisco and so on are also making some, it's hard to figure out because it's in some ways against their proprietary interests, but they
Yep.
are embracing OpenFlow to some extent,
Yep.
perhaps reluctantly. So
Yep.
how much cheaper is it? If I say I'm using OpenFlow, is it cheaper today, or is it just as the promise of commoditizing
Oh,
the switch?
I don't know the numbers off the top of my head, but yes, it is a lot cheaper, even today. Because especially in these data centers, a lot of these data centers do use OpenFlow because of the network savings that they get. And I wish I had some numbers
Do you know who they buy it from? Like, who are they buying these switches from? And so you said a lot cheaper, who do they get it from? Are they from the same vendors? It's just the OpenFlow version of the switch, or is it something new?
I can't say that at the moment. I'll have to look that up. Anyone else? Yeah.
Did you try combining the two, like the hardware encapsulation and the hardware firewall?
No, but that's something that would be interesting.
Yeah.
Again, off the top of my head, I expect the throughput to be the same and probably slightly higher latency. But Braden?
This might be a question slightly more geared towards Stuart, so I don't know if you know
Okay.
the answer to it, but can you redirect from one VFR to another VFR in the same FPGA? And if so, does it actually go to the network and come back, or just go to the second VFR?
Actually, so not in this infrastructure that we have, but for a course project last semester, I actually did implement
Okay.
that. So yes, now if I had that new infrastructure, yes, if in the static region when the packet's being outputted, it actually checks, hey, before I output it to the network switch, is the application on this same FPGA? And if it is, then don't go through the switch.
Okay, that's cool.
Yes.
You touched on this very briefly, when you spoke about heterogeneous and that concept. So when you're talking about splitting the FPGA into multiple blocks, are they just the different VFRs meant for the routing, or is the user able to do something else on the FPGA as well if there's space left over? Because it's essentially just a virtualized FPGA. So
Yes.
do you virtualize other functions on it, or is it really just virtualizing the VFRs for the
Well,
switching stuff?
you can program anything you want on these VFRs. Like in this case, I'm using it for the VXLAN tunneling and the VXLAN firewall. But ideally,
Doing something other than networking completely.
yeah.
So it is possible to do that. So
Yeah.
Yeah, I think the only constraint is in this environment, that input and output is via the network.
Mm. So somebody else could say, hey, you know what, if there's FPGA left over, I want to make another block in here, process something else, and take advantage of the fact, like Braden mentioned, that you're not moving stuff in and out again. So here you have a high bandwidth FPGA just sitting there and might have space to do something else.
Yeah, I think some of the sort of future applications we're looking at is sort of in the computing domain, and so we're looking at how to, connect multiple FPGAs together so that we can do one computation.
I guess just to follow up on that, how much space was used on the FPGA to perform like the firewall task? How big was that circuit?